Hi everybody. We're going to be doing section 8.3, the method of undetermined coefficients annihilators. Okay, so what we're going to do is we're going to learn to solve a certain class of non-homogeneous nth order linear differential equations. In other words, it's going to look like this. P of D, remember, P of D, this is our polynomial differential operator. P of dy is equal to f of x. And I'm going to call this differential equation star. We'll come back to this a lot, where capital F of x takes on certain forms. We're not going to learn how to solve this given any function on the right, but only particular functions. Okay, we'll find out which ones in a little bit later, okay? So let me remind you of something we learned in 8.1, because 8.1 and 8.2 are both going to come into play very seriously in this section. So recall that in 8.1, we learned that the general solution of star always looks like this: yc plus yp. What do these two things stand for? Well, yc is the general solution to the associated homogeneous equation P of dy equals 0. And yp is a particular solution to star. Okay, so we need the yc, which is the solution to the associated homogeneous equation, and that's something you guys already learned how to do in the last section. So let's move on here. We know how to find yc since, remember, P of dy equals 0 has constant coefficients, i.e., we learned how to do this in section 8.2. So new question then. The only thing we don't know how to do is how do we find yp for our differential equation star? To answer this, we introduce annihilators. Okay? So what is an annihilator? So we need a definition. An annihilator of a function y is a polynomial differential operator A of D such that A of D applied to y is equal to 0. Okay, so I want you to think of an annihilator as being a differential operator that completely takes out the function. Okay, it wipes the slate clean, and when you hit it with it, you get 0. Let me give you an example. Okay, we all agree that if you take a derivative, say, of a number, you get 0. What happens if you take two derivatives of, for example, the number or the function 5x? So what is the second derivative of 5x? Well, this is the same as the first derivative, right? If you take a derivative of 5x, then that leaves you with 5. And then if you take a derivative of 5, you get 0, right? So what does this mean? This means that d squared annihilates the function 5x. That's just an example of an annihilator. But let's get a little bit more interesting in a way that it relates to some differential equations that we've already seen. So since we know that a differential equation d minus 3y equals 0, we know that this guy from section 8.2 has solution y equals any constant times e to the 3x, right? I could put any constant in front. I'm just putting a 1 in there for now. But think about what it means. For this to be a solution to that, this means that d minus 3 annihilates e to the 3x. Likewise, if you recall from that section, if we have a repeated root, we know that d minus 3 squared, for example, annihilates x e to the 3x, right? Since x e to the 3x is how you get a solution to d minus 3 squared times y. So in general, this leads us to one important fact. D minus a to the power of k plus 1. You notice you always need one more power to kill an x. So d minus a to the k plus 1 annihilates x to the k e to the ax. Okay, including all lesser powers, okay? Okay, so this is an important fact. I'm going to box this in red because this is something that we're going to be referring to quite a bit, okay? So d minus a to the k plus 1 annihilates x to the k e to the ax. For example, just to throw in a quick example, if you had, let's say, x to the 7th e to the 4x, then this function has annihilator d minus 4 to the 8th power, right? All we're doing is we're using that formula up there, okay? Now, that's one type of thing that we studied. And what about the sines and cosines? Remember, sines and cosines appear when our roots are imaginary, right? So, recall, for example, if z is equal to, let's say, let's give a concrete example here. How about 5 minus 2i? Or let me do 5 plus 2i. If 5 plus 2i, actually they have to appear in conjugate pairs anyway, right? So if z equals 5 plus 2i, since d minus z times d minus z bar, remember they always appear in complex conjugate pairs, right? Since that guy, remember we learned in the last section that this guy has solutions e to the 5x cosine of 2x and e to the 5x sine of 2x. Okay, since that's true, then we could say that d minus z times d minus z bar annihilates both e to the 5x cosine of 2x and e to the 5x sine of 2x. So if we want to just do this in general, because I know I did this with particular numbers 5 and 2, in particular, so I should say in general actually, d minus z times d minus z bar to the k plus 1 annihilates both. You'll notice that I have an x to the k e to the ax cosine of bx and x to the k e to the ax sine of bx. Again, this is a general formula that we're going to use all the time, so I'm going to put a box around it, okay? So these are the two main annihilator formulas that we have to know. We have to know how to annihilate sines and cosines, and we also have to know how to annihilate just exponentials. Again, if you have an x to the k, you just need to raise the other guy to a necessary power in order to annihilate it. Okay, so this is why when you see an x to the k on both of these, you need a k plus 1 up there. And of course, this includes, so let me just say including lesser powers of x. In other words, if you had x to the 5th times that stuff, and you had an annihilator for it, of course that's also going to annihilate smaller powers, like x to the 4th, 3rd, and so on. Okay, so this will be important when we come back to this later. So what I'm going to do is, before writing a step-by-step approach for how to do this method, I'll illustrate with a simple example. This will be an easier example than you will probably get on homework and stuff, but this will just be our first example. I'm going to do some tougher ones as well. Okay, so here's our example. Our example is to solve the differential equation y double prime plus y prime minus 6y is equal to 10 e to the 2x. Okay. So we notice this is not homogeneous, right? If it was homogeneous, you'd have a 0 on the right. Okay, so this is how we know we're going to have to use this method. But the first thing we do is always begin by writing down the associated homogeneous equation. Okay, so what is the associated homogeneous equation? The associated homogeneous equation would be y double prime plus y prime minus 6y is equal to 0. So what we're going to do is we're going to find yc. Okay, how do we find yc? Remember, we've got to write out this guy. This is really d squared plus d minus 6 times y is equal to 0. Or we can factor this. This factors into d plus 3 times d minus 2 times y is equal to 0. Okay. Sorry, I actually wrote the wrong problem down. Let me change this example. Let me just make this a minus sign, okay? Let me do that. Sorry, I didn't mean to do this example. This would have made the example a little harder than I wanted for the very first one, okay? So this would be a minus here, and this would be a minus then, and this would be a plus. And so what do we end up with from here? This implies that we get yc right away. Remember, it's c1 e to the 3x plus c2 e to the negative 2x. Okay, so start off by doing that. I'm going to, underline this guy. We'll come back to it later because we're going to need it, okay? Now what? So the trick now is to take our differential equation up here, and we're going to apply the annihilator. So let me ask you this. What annihilates this right side? So note, d minus 2 annihilates 10 e to the 2x. So what I'm actually going to do is I'm going to apply the annihilator. So I'm going to apply d minus 2 to our differential equation. So what is our differential equation? Can't I write our differential equation like this? D minus 3, d plus 2, y is equal to 10 e to the 2x, right? So what I'm going to do is I'm going to apply, let me give this a little space here. What I'm going to do is I'm going to apply the annihilator d minus 2 to the left, and I'm also going to apply it to the right. And I do that because that's going to annihilate the right side. So that gives me a 0 there. And now I'm left with d minus 2, d minus 3, d plus 2, y is equal to 0. So what we need to do now is figure out the particular solution, right? So what I'm going to write is the following. yp. Remember, this is going to be a solution to the entire differential equation, right? So let's see what we get. We know we get c1 e to the 2x plus c2 e to the 3x plus c3 e to the negative 2x, right? This is what we get. But here's the thing. Two of these guys are already occur in the YC, right? This guy and this guy are repetitions because they're already included in there. So the only... Oh, sorry, I crossed off the wrong one, didn't I? Yes, I meant to cross off this one and this one, right? Those two are already included in that. So the only new one is this. So this is the one that we need to write down, okay? So this is what we call a trial solution. So a trial solution, I'm going to use another letter for the constant, okay? Yp is equal to, many times they use a naught, so I'm just going to go ahead and copy the notation of the book. So it's a naught e to the 2x. This is a trial solution, okay? It's called a trial solution, and a naught, this a naught right here is called an undetermined coefficient. This is where this section gets its name. What we need to do is to find a naught now, because actually not every value of a naught will work. Okay, so what we need to do is we need to find a naught, and we're going to do that by plugging Yp into the differential equation. Did we call it something? Well, let me call it star. We're going to plug it into star. Okay, so let me go ahead and take some derivatives of that because we're going to need to plug it in, right? So what is Yp prime equal to? It's 2a naught e to the 2x, right? And what is Yp double prime equal to? If we take another derivative, we get 4a naught e to the 2x. So now we plug it all into the original differential equation and we end up with the following. We get y double prime, so it's going to be 4a naught e to the 2x plus y prime, so that's plus 2a naught e to the 2x minus 6y, so minus 6a naught e to the 2x. All of that is going to equal 10 e to the 2x. Oh, sorry, I forgot that I changed my original problem. Remember, I changed it to a minus sign, so that should say minus there. There we go. So the idea here is that we can actually divide everything by e to the 2x because that's never 0. And now we're just left with 4a naught minus 2a naught minus 6a naught is equal to 10. And now we can just solve for a naught. This is negative 4a naught is equal to 10. And so a naught is equal to negative 5 over 2. And so this gives us our Yp. Our Yp is equal to negative 5 halves e to the 2x. Okay, remember our Yc from before, so if this is Yp, it's right there. And remember our Yc is back here. I already underlined it, right? And so our general solution, we're ready to write it down. So this implies that y is equal to, let me write it just how I had it before. I had c1 e to the 3x plus, then I had c2 e to the negative 2x plus, and then I had, oh, that's right here. And then I had minus 5 halves e to the 2x. This is our differential equation solution. So remember what I've done, this part up here, these first two, this is yc, and then right here, This is yp. Okay, so it's all yc plus yp. Now that we've seen one example of this, and this was a simple example because there's a lot of things that could have gone wrong, and I want to show you guys the extra modifications that need to happen. But what I'm going to do now is write out the steps. So these are going to be the steps for using annihilators to solve P of D times Y is equal to capital F of X. Again, we're going to call this star. So let's write out the steps. Now that we've seen it once, hopefully this should make sense. So step 1, we're going to find YC by solving the associated homogeneous equation P of D y equals 0. Again, that's what we learned in the last section. Step 2. Apply the annihilator A of D of the function. You're always going to apply it to both sides of star, leading to A of D, P of D, Y is equal to 0. Okay? I'm going to go ahead and call this guy star star. Okay? Step 3. We're going to set up YP now, which remember, this is called, I believe I told you what this was called, but this is called the trial solution, okay? So we're going to set up YP, and the way we do this is we find the general solution to star star, right? So remember, we found the general solution to star star, except we're going to leave out the terms that already appear in YC. Okay, so you do not leave those terms in there. Okay, and step 4, okay, what you're going to do is you're going to find YP, right? Once you set it up, you're going to find YP, and you do this by solve for all undetermined coefficients by plugging YP into your original differential equation, star. Okay. There is one note that I want to write down before we begin this process. So note, what if capital F of X, what if your function has more than one of the above types? So if capital F of X is the sum of two or more of the above, then just multiply all necessary annihilators. Okay, so this is just saying that if we have more than one, you're just going to multiply all the necessary things that you need together, and that'll end up annihilating the whole thing. Okay? All right, so I want to do some more examples here. So let's start another one. I want us to solve the following. Y double prime minus 2y prime minus 3y is equal to 2e to the 3x. Okay, it helps to take this differential equation and immediately rewrite it using differential operator notation. D squared minus 2d minus 3 equals 2e to the 3x. And I'm going to call this guy star. So we're going to start off by finding YC. And remember, YC is the solution to the homogeneous one. So I'm going to write the homogeneous one, and I'm going to also go ahead and factor this in one step. This would factor into d minus 3 times d plus 1, right? So this is the associated homogeneous equation, right? So this is how you find YC, is we have to solve this guy. So we have two different roots here, and so we know what to do. YC is equal to C1 e to the 3x plus C2 e to the negative x. Okay? Now we're going to apply the annihilator to both sides of the above equation. So what annihilates 2e to the 3x? We know that d minus 3 annihilates 2e to the 3x. So what I'm going to do is actually apply d minus 3 to both sides. But I hope we notice that this actually gives us a d minus 3 squared. So when we write down yp, what are we going to get here? Well, remember, when we get a repeated root, let's think back to section 8.2. When we get a repeated root, we actually are going to have several terms, right? We're going to have, first we have an e to the 3x term. Then we have an x e to the 3x term. That takes care of our multiplicity. And then we have an e to the negative x term, right? So I have a C1, I have a C2, and I have a C3. But don't worry, our YP does not need all of those because we throw away the terms that already appear in our YC. So I notice that I have this term that appears, and I notice that I already have this term that appears. So all I really need is this extra x e to the 3x term. So this is our trial solution. So our trial solution is going to be yp is equal to, let's use a naught, because again, this is the notation they like, a naught x e to the 3x. Okay. So what I'm going to do now, again, is plug that into, so we're going to plug yp into our differential equation, and to do that, I need to take a couple of derivatives. So what's yp prime? To do this, I'm going to need to do the product rule, right? So it's going to be the derivative of the first. I'm going to look at the product like this. The derivative of the first times the second plus the first times the derivative of the second. So I know I'm going to have an extra 3. So it's going to be 3 a naught x e to the 3x. Okay. What is yp double prime going to equal? I take another derivative, right? So this derivative is going to be 3a naught e to the 3x plus, and again, I'm going to use the product rule on this. This is going to be the derivative of the first, which is 3a naught times the second, plus the first times the derivative of the second. It's going to be 9a naught x e to the 3x. But these two are like terms, so I'm going to combine them, and I get 6a naught e to the 3x plus 9a naught x e to the 3x. So I got my yp prime, and my yp double prime. I'm going to plug them all into so plug into star. What do we get? We end up with, first you do the double prime, so I get 6a naught e to the 3x plus 9a naught x e to the 3x minus 2 times y prime. So I'm going to do minus 2 times each of those as I write it down. So minus 2, and then I have a minus 6, and then I have minus 3y is that equal to 2 to the, this has to equal 2e to the 3x. Okay. So what happens? Well, let's get rid of the e to the 3x, right? Because I can divide the entire thing by e to the 3x, and that's going to be gone. But also, we notice that 9a naught x e to the 3x actually cancels with these two, right? These are all like terms and they go away. And so from this we get the following. 4a naught, again I'm dividing also by e to the 3x, is equal to 2. What does this mean? This means that a naught is equal to a half, and so we know what our particular solution is. It's 1/2 x e to the 3x. So we got our yp, we got our c from before, so this implies that y, remember y is equal to yc plus yp. Yc from before was c1 e to the 3x plus c2 e to the negative x plus 1/2 x e to the 3x. This is our general solution to the differential equation. Okay, we've done a couple of examples, but I want to do some more complicated ones now. So guys, I think the hardest part here is how to set up the trial solution. The rest is just taking derivatives and plugging stuff in and solving. So what I want to do from now on is sort of stop at this point, okay? So that way we can practice doing lots of examples and just setting up trial solutions. So for all the following ones, we're going to stop at this point. We're not going to keep going because I'm assuming you guys know how to plug in and just do algebra, okay? So let's do some examples of just the setting up part. So example, I want us to set up a trial solution for y double prime minus y prime minus 2y is equal to 10 sine x. We haven't done one yet with sine and cosine, so this will be good practice. Okay. Let's go ahead and write this as in differential operator form. So this is the same as d squared minus d minus 2 of y is equal to 10 sine x. This is the same as d minus 2 times d plus 1 y is equal to 10 sine x. Okay. Let me keep this on its side here, right? Okay, so we know then, let's just do this a little bit faster, right? We know that yc is going to be, we know that that's going to be to set this guy equal to 0. And so we know that this is going to be c1 e to the 2x plus c2 e to the negative x. Okay. Now, what am I going to apply to annihilate 10 sine x? Well, remember what we said? We said that we always know how to annihilate it based on what the e power is and what's attached to the b, right? So what we are seeing here is that this guy is the same as e to the 0x sine of 1x, right? So this guy is our a, and this guy is our b, right? So we know that this is going to be the imaginary number a plus bi, but since a is 0, it's just going to be 1i or just I, right? Okay. So what does this mean? So this means that d minus I times d plus I annihilates 10 sine x. You could multiply that out, okay, and you could write that as d squared plus 1, but you don't really need to, okay? So what we end up with now, if we apply the annihilator to the entire differential equation, we get d minus I times d plus I times d minus 2 times d plus 1 y is equal to 0. So what is our trial solution going to be? So guys, since we've done a few examples already, of course, you notice that we keep writing stuff down that we don't need to, right? So what we've been doing is every time I've been writing stuff down that I don't need and then crossing it out later. But we could just omit them as we write down now that we're getting a little better at this, right? So let's think. I'm obviously not going to write down the 2 and the negative 1 because those already are obtained in yc, right? So yp is just going to be, remember I have a plus or minus I, so we know that that's going to be a naught cosine x plus a1 sine x. We actually have 2 undetermined coefficients. 2 undetermined coefficients. So okay, so your undetermined coefficients are a naught and a1. And from there, all you would need to do is take derivatives and plug them into the original. And then from there, you could figure out what a naught and a1 have to be. Because there's 2 unknowns, you actually are going to have a system of equations that you set up here. Okay, so this is how you would do a trial solution for sines and cosines. But we're going to do many more examples because I want us to make sure that we understand this. Okay, so let's try another one. Set up a trial solution for d squared plus 4y is equal to 9 cosine 2x plus 3 sine 2x. This is going to be a little bit more complicated, okay? All right, so let's start by setting up the associated homogeneous, right? So the associated homogeneous equation is, of course, d squared plus 4y is equal to 0. What are the roots of d squared plus 4? Well, if you were to solve r squared plus 4 equals 0 here, of course you get plus or minus 2i, right? So you do get two imaginary solutions. So then what would yc be? Remember, we learned this again in the last section. This is going to be, because we have a 0 real part for this imaginary number, we do not need any e's here. It's just going to be c1 cosine of 2x plus c2 sine of 2x. That's going to be our yc. Now what? We're going to apply the annihilator. So let's think about what annihilates this. Notice that that's a cosine 2x and that's a sine 2x. Okay? So what's going to annihilate that is exactly d minus 2i and d minus 2i bar, which is really d minus negative 2i. Okay? But it's going to be the exact same thing that we already have on the left, right? Because that just multiplies to d squared plus 4. Okay? So this guy is the annihilator. This guy is the annihilator for f of x, right? Remember, this whole right side we call f of x, right? We're saying that the annihilator is d squared plus 4. So we apply it to both sides, and we end up with the following. D squared plus 4 squared y is equal to 0. Now that it's squared, we know from the last section that we're actually going to need to keep going up in power, right? So what would yp equal? Well, I know that I have to I know that I'm going to have this. I know I'm writing unnecessary stuff right now, but I want to make sure that you all understand what's going on. So I need all 4 of these, right? Oops, I forgot the x at the end, right? Okay, why do I need these x's? Because I have this repeated root here. Remember, you need to throw in as many x's. If that was a 3, I would have thrown in an x for both and then an x squared. Okay, but these are all 4 of the linearly independent solutions. However, I don't need these 2 because they're already contained in our yc. Remember, we only write the necessary ones. And so our trial solution that we would need to then go further with is yp is equal to, I'm going to give these constants new names, a naught x cosine 2x plus a1 x sine 2x. This would be our trial solution. Again, take 2 derivatives of that, plug it into the original differential equation, and then you can figure out what a naught and a1 are. So again, important reminder, you must determine the coefficients of yp to solve star. Remember, star is the original differential equation. I'm not solving them now. I'm just finding the trial solution. But remember, for the actual problems in the book and exams and quizzes, you do need to go all the way and actually solve the differential equations. Okay? We're going to do 2 more setups. This is good practice. So again, set up a trial solution for the following: d squared minus 4d plus 5 y is equal to 8x e to the 2x cosine x. Okay, So if we look at the associated homogeneous equation, we know that this guy is d squared minus 4d plus 5y is equal to 0, right? So this is what we need to solve to find yc. But you can't factor that as much as you try, and so we need to use the quadratic formula, right? So this becomes 4 plus or minus the square root of b squared, so 16 minus 20 all over 2, which is the same as 4 plus or minus, this becomes 2i all over 2, which is the same as 2 plus or minus I. Okay, so what would yc be? Yc is equal to c1 e to the 2x cosine x plus c2 e to the 2x sine x. Again, if that confused you, you really need to go back to section 8.2 because that's where I'm getting this from, okay? That's how we translate these imaginary solutions to actual solutions to the differential equation. Now what? Now we need to figure out what the annihilator for the right side is. Don't let that x confuse you. If you were to cover up that x, we know that we have to have e to the 2x cosine x. So doesn't that look familiar? That's exactly what we have in those other terms, right? E to the 2x cos x and e to the 2x sine x. So we know that d minus, so if we call z 2 plus I, we know that d minus z times d minus z bar is going to, oh, now let's be careful though. That would annihilate it if there was no x there, but because there's an x there, I do need to square it out, right? So this guy annihilates 8x e to the 2x cosine x. But what is that, guys? This is exactly the guy that I already had to start off with. I know that because when I solved it, I got those exact same imaginary numbers, right? I mean, you could multiply d minus 2 plus I times d minus 2 minus I, but this is what you're going to get, okay? So I know that I'm going to need to hit it with d squared minus 4d plus 5 squared on both sides. So if I hit it with the square, I actually end up with a cube. Okay, so again, I applied that guy, so we apply 2 star, right? And that's where we got this equation from. So now what? It's pretty much what we've been doing, except you see a cube there. So we know that we're going to have to throw in those extra powers. So I hope what I'm about to write makes sense. I'm going to skip the powers that are already in YC. I don't need them, right? So let's just throw in the ones that we do need. I'm going to put A naught e to the, I just said I was going to skip it, right? So I've got A naught x e to the 2x cosine x plus A1 x e to the 2x sine x. So that takes care of one, but the thing is, I have a cube, so I need another one. Plus A2 x squared e to the 2x cosine x plus A3 x squared e to the 2x sine x. So this would be our trial solution. I'm hoping that makes sense, okay? Again, we need to go up to the x squared term because we have a cube there. However, I could leave out the first ones because they were already being taken into account in my YC. So again, if we wanted to go further and actually solve the differential equation, I would need to get this guy, plug it back into my original differential equation, solve for all four of those constants in there, and then remember, that's just your YP. You would add it to your YC, right? That's how you would write down the final solution. Okay, we're going to do one more. This one's really tough. If you can understand this one, then you can pretty much do anyone, okay? So last example, I want us to set up a trial solution for the following craziness. D plus 2 squared times d squared plus 16y is equal to 4x e to the negative 2x plus 8 cosine of 4x plus e to the 3x sine of 2x. Okay, lots going on here, right? So at least it's already factored for us, right? So let's start by finding YC, and we're going to write down the associated homogeneous equation. That's going to be d plus 2 squared times d squared plus 16 of y is equal to 0, right? So we can already write down our YC. Our YC is going to be c1 e to the negative 2x, but it's squared, so we need another one with the x term there, right? So plus c2x e to the negative 2x. And then if you solve r squared plus 16 is equal to 0, you get r equals plus or minus 4i. And so our next two are going to be c3 cosine of 4x plus c4 sine of 4x. All of that is our YC, okay? So that's going to be important later when we set up our trial solution. So now we need to find the annihilator. This is the tricky part because we've got three things there. So what do we need to annihilate? Let's go step by step. So I'm going to look at this guy first. I've got a 4x e to the negative 2x. So what's going to annihilate that? It's going to be, I need a d plus 2, right? Because remember, it's always d minus whatever that exponent is. But I need it to be squared because I've got an x term in there. Next, I need to annihilate the second guy. You notice that that's a cosine of 4x. So again, that is, I know I'm going to need a d minus 4i for that, times d minus negative 4i. So in other words, I'm going to need exactly the d squared plus 16 to annihilate that guy. Now this guy, this is a different complex number. If this was a sine 4x and there was no e to the 3x there, it would already be annihilated by the thing I just wrote down. But this is going to be different, right? So what annihilates that guy? So that guy, I want you to think about this, right? In our complex number world, when you have an e to the 3x sine of 2x, we know that the complex roots are going to be 3 plus 2i and 3 minus 2i. So if we let this guy be z, and then that guy would be z bar, we know that this guy is going to be d minus z times d minus z bar. So everything I just wrote down annihilates capital F of x. Again, you notice I didn't even bother multiplying z times z bar because it's not going to matter, right? We know what the form is going to look like, but let me just go ahead and jump now. So remember, we are going to apply to star. Yes, we're going to apply all of that to this, okay? And so here's what we end up with. We just applied a d plus 2 squared, right? But we already had a d plus 2 squared to begin with, so now we have 4 of them. We end up with d plus 2 to the 4th. D squared plus 16, we already had a d squared plus 16, so now we have a d squared plus 16 squared. And then we have this d minus z times d minus z bar. All of that equals 0. So we're ready to write down our trial solution. Okay, there's going to be a lot of stuff, though, that's already taken care of in our YC. So let's start with d plus 2 to the 4th. So I'm going to need to go up to x cubed, but I've already got the nothing and the x term taken care of in our YC. So because these first two are already there, I only need the last two. So I'm going to write a naught x squared e to the negative 2x plus a1 x cubed e to the negative 2x. That's my first two. Okay. Those are my last two. Now I'm going to go to d squared plus 16 squared. So that's going to give me the sine and cosine terms, except I've already got the first two taken care of from this, right? So I'm only going to need the ones with x in it. So it's going to look like this, plus a2x cosine of 4x plus a3x sine of 4x. And now I've got to take care of my d minus z bar. Again, I didn't bother actually writing those down because we already know what the roots are. They're right here, right? So those guys have those as my roots. So I can already write down what those answers are going to be. It's going to be plus a4 e to the 3x cosine of 2x plus a5 e to the 3x sine of 2x. And there you have it. We wrote down our whole trial solution. Again, in an ideal world, you would take derivatives of that, plug it into the original, and figure out what all of your coefficients are. This would be way too much work for a human. This is more for a computer to do because these derivatives would get really nasty, especially these triple product rule ones or double product rule, sorry, but still, this wouldn't be fun at all. I know it was a long video, guys, but I wanted to do lots of examples, and I'm hoping that the method is clear now. Thank you very much for watching.